is me Shivali here, back with the part 1, 2, 3, 4. Yeah, we have completed almost 3 parts, and now we are here in the fourth part of our chapter. This is electrochemistry of class 12. So, electrolytic cell is the last topic we have to discuss in this chapter. We have already discussed the electrochemical reactions and electrochemical cells, right? So, what is the reaction taking place in electrochemical reaction? It is the conversion of chemical energy to electrical energy. Yes, it's a conversion of chemical energy to electrical energy, and such cells are known as galvanic cells or voltaic cells. So I've already told you that in this chapter we'll be dealing with both electrochemical cells and electrolytic cells, but majority of the chapter is talking about the electrochemical reactions, and then in this part 4 we are going to deal with electrolytic cells where the conversion is from electrical energy, and by using electrical energy we create chemical changes. Okay, so electrolytic cell in electrolytic cells, the chemical energy that happens by the passage of electrical energy is discussed. Okay, by the passage of electrical energy or by the passage of electricity, we bring about chemical changes in a setup. Okay, by the passage of electrical energy or by the passage of electricity, we bring about chemical changes in it. So it's a conversion of electrical energy to chemical energy, and such a conversion is known as electrolysis, and the device performing such conversions, or the device performing electrolysis, is known as electrolytic cells. So electrolysis is a process of conversion of electrical energy to chemical energy, and the devices performing electrolysis is known as electrolytic cells. So electrolytic cells mainly work with Faraday's law. Okay, they mainly work in the principle of Faraday's law. We have two laws of Faraday, that is Faraday's first law of electrolysis and Faraday's second law of electrolysis. We'll be discussing both laws. In the first law, we need the statement, we need the equation, also we need to know how we'll be dealing with the numericals coming from that part of Faraday's first law of electrolysis. So from the Faraday's second law, we just need the statement and the equation. No numericals will be asked from that topic. So now we are going to discuss the purification of copper by electrolysis. You know what is electrolysis, right? Electrolysis is a conversion, or the process of conversion of electrical energy to chemical energy. And now we are going to explain the process that's going running in a electrolytic cell. Okay, how the electrolysis takes place in an electrolytic cell, and for that, for explaining the process happening in electrolytic cell, we use the example of purification of copper. So consider a beaker. Okay, I have two electrodes here. This is the impure copper. This is the pure copper, and both are connected to a battery. This is a positive terminal of the battery, and this is a negative terminal of the battery. So this is the impure copper, right? Impure copper, which is actually the anode, having positive charge. This is the pure copper, which is having negative charge, and it's a cathode. I'm having an electrolyte here, and maybe it is copper sulfate. Okay, also some amount of impurities from the impure copper is deposited here, that is the impurities. So one of the differences between electrolytic cell and electrochemical cell is that in electrochemical cell we have learned a trick, LOAN, which means loss of electron in the left side, O for oxidation, A for anode, and N for the negative charge, which means in electrochemical reactions, anode is assigned the value of negative charge. Okay, it is assigned a charge of negative. Okay, a negative charge, a negativity is assigned to anode. In the case of electrolytic cell, okay, anode is assigned a positive charge, because it is connected to the positive terminal of the battery. Anode is positive here, cathode is negative here. Okay, so keep in mind, in the case of electrochemical reaction, it is lone, left side, loss of electron, O for oxidation, F for anode, and N for negative charge. In the case of In the case of electrolytic cells where electrolysis takes place, L for left side, loss of electron, O for oxidation, A for anode, and it is in positive charge. Anode is positively charged. P for positive. So keep this in mind. Lone for electrochemical reactions, lope for electrolytic reactions, electrolytic cells. So here, from the impure copper, okay, from cathode, so we need to know how it happens, right? How the process of conversion of impure copper is, the process of converting impure copper into copper takes place. So impure copper is there in the anode side. In anode, oxidation takes place. So anode, oxidation takes place where copper turns to copper 2 plus by giving 2 electrons. By giving 2 electrons, copper changes to copper 2 plus. At cathode, the copper 2 plus accepts the 2 electrons from the anode side and it changes to copper itself. Okay, so the impure copper is converted to copper and the impurities are deposited here. Impurities are deposited there. So this is a process of electrolysis taking place in electrolytic cells, and we have explained it with an example of purification of copper, conversion of impure copper to copper. Now we're going to deal with the Faraday's first law of electrolysis. Faraday's first law of electrolysis, before coming to this statement, let me explain it with an example of the copper itself. So copper, consider the impure copper, the amount of impurity, the amount of, or consider case of cathode, the amount of pure copper depositing on the cathode, okay, is directly proportional to the current flowing through it. Or the amount of impure copper liberating from the anode side is directly proportional to the current flowing through it. So this is itself saying in the Faraday's first law of electrolysis. Let me read it for you all. The amount of any substance deposited or liberated at the electrode is directly proportional to the quantity of electricity passing through the electrolyte. Okay, so the amount of pure copper deposited on the cathode side is directly proportional to the electricity passing through it. The amount of impure copper liberated from the anode side is directly proportional to the electricity flowing through it. In general, the amount of a substance deposited or liberated at an electrode is directly proportional to the electricity passing through the electrolyte. So let the amount, the quantity of the substance deposited or liberated be W. It is directly proportional to what? It is directly proportional to electricity. So let me represent or denote electricity as Q, where Q is a charge. You know what's the the equation of charge, right? Q equal to IT. Q in coulombs, IT. I is a current in amperes and T is a time in second. Okay, so W directly proportional to IT. Removing the proportionality, I introduce a proportionality constant which is equal to ZIT. This is my equation. W equal to ZIT, where Z is the proportionality constant. Here it is called as electrochemical equivalent. I is a current and T is a time in seconds. So W is a quantity of a substance deposited or liberated from an electrode while electricity is passed through it. And the electricity is denoted here in the form of Q, charge. Charge is equal to current into time. Q equal to IT, and Z is a proportionality constant called electrochemical equivalent. There is an equation to find electrochemical equivalent, that is equivalent mass divided by 1 Faraday, 96500. Okay, equivalent mass divided by 96500. So we know that electrochemical equivalent is a constant, proportionality constant. So I'm asking you a question like, what is electrochemical equivalent? How will you define it? How are you going to define it? We know the equation W equal to ZIT. Let us simplify it to ZQ, right? W equal to ZQ, where Q is a charge. It is similar to I into T, current into time. Z into Q, right? So when Q equal to 1 coulomb, W equal to Z into 1, that is W equal to Z itself. W equal to Z itself. So from this we can define electrochemical equivalent as the amount of substance deposited or liberated at the electrode when 1 coulomb of charge is passed through it. A question is given here. A solution of copper sulfate, CuSO4, is electrolyzed for 10 minutes. 10 minutes time equal to 10 minutes into 60 seconds with a current of 1.5 amperes. Current I equal to 1.5 amperes. We need to find the mass of copper deposited at the electrode. The equation for this is W equal to ZIT. And we need to find Z, right? Z, equivalent mass by 96500. Equivalent mass by 1 Faraday, which is 96500. Equivalent mass of copper is 31.8, and 965 divided by 96500 will give you 0.29. So just put those values in the equation and find the answer. Now coming to Faraday's second law of electrolysis, very simple. You just need to study and remember the statement of the equation. When same quantity of electricity is passed through different electrolytes. Here I have a beaker. In this beaker I have two electrodes. On the other hand, I have the second beaker. In that beaker I have two electrodes. My solution is here, the electrolyte. Okay, so the law tells you that consider same amount of electricity is passed through the beaker 1 and beaker 2, or the electrolyte 1 and the electrolyte 2. The amount of different substance is deposited at the electrode. The amount of substance is deposited at the electrode is directly proportional to their equivalent mass. Equivalent mass. Very simple law. So when I consider a beaker and other beaker, if the electricity passing through those beakers are equal, the amount of substance deposited at their electrodes will be directly proportional to their equivalent masses. W1 by W2 equal to E1 by E2, where W1 and W2 are the masses or the quantity of the substance deposited, and E1 and E2 are their equivalent mass. Okay. Now coming to the topic of battery. You're really familiar with the topic battery or the word battery itself, right? Every day you're dealing with some of the other battery in your life, in watch, in clock, in phone, in electronic devices, digital devices, everything, laptop. So in all the electronic devices, there is battery. So some batteries need charging, recharging, right? And some batteries, it's one-time use, one-time usable. So what is the conversion taking place in battery? Is it chemical energy to electrical energy or electrical energy to chemical energy? In battery, we deal with the reaction or the chemical conversion of chemical energy to electrical energy. In battery, we are dealing with the conversion of chemical energy to electrical energy. So there are two types of battery, as I already said, primary battery and secondary battery. And batteries, in batteries, redox reaction is taking place. That is reduction, oxidation, reduction reaction. It is a conversion of chemical energy to electrical energy. We have two types of battery, that is primary battery and secondary battery. Primary battery is just that we can't recharge it, we can't reuse it because the reaction can't be reversed. Okay, as we can't reverse a reaction, we can't reuse it, we can't recharge it. So primary battery examples are dry cell, mercury cell, which are used in clock, watch, etc. So secondary battery is just the opposite of primary battery, because in secondary battery we can reverse the reaction, so we can recharge it, so we can reuse it. Okay, it's rechargeable, reusable, we can reverse the reaction. In primary battery we can't reuse it because we can't recharge it, because we can't reverse the reaction. So examples of secondary battery are lead storage battery, nickel cadmium batteries, big type of batteries you might have seen in your household, in inverters, automobile industry. Okay, so now we are going to deal with the dry cell. Dry cell is an example of primary battery. You need to know the anode of dry cell, cathode of dry cell, the cell potential of dry cell, and also the electrolyte used in dry cell. So we are going to deal with 3 to 4 batteries in this session. In all those batteries you need to keep in mind the anode, cathode, the electrolyte, and the cell potential of each batteries. So dry cell, the anode is zinc, and the cathode is carbon with manganese dioxide. Okay, electrolyte is a paste of ammonium chloride and zinc chloride. It's a paste of ammonium chloride and zinc chloride, and the cell potential is 1.5 volt. Simple. Yeah, I know it's a little bit of by hearting stuff. Mercury cell. In mercury cell, the anode is zinc mercury amalgam, an amalgam of zinc and mercury. In mercury cell, the anode is an amalgam of zinc and mercury. The cathode is a paste of HgO and carbon. And the electrolyte is a paste of KOH and zinc oxide. Okay, ZNO. And the potential is 1.35 volt. So all these are examples of primary battery. We need to know about the secondary batteries too. In secondary battery, nickel cadmium battery is okay. The lead storage battery having long life, expensive. Yeah, mainly expensive. Okay, so we'll deal with the anode, cathode, electrolyte of nickel cadmium cell. The anode is cadmium, as already mentioned in the name, nickel cadmium. The cathode is NiO2, as I already mentioned in the name, nickel. Okay, electrolyte is a moist form of NaOH and KOH. In the case of lead storage battery, which are mainly used, the batteries which are mainly used in inverters, anode is lead. Lead is the anode. And the cathode is actually lead itself, but a grid form of lead. Grid form, okay? Grid form of lead with lead dioxide. And the electrolyte is 38% solution of sulfuric acid. Now coming to fuel cells, which is a must-learn topic in electrochemistry. Fuel cells actually they produce electrical energy. They produce electricity by the combustion of gases like methane, hydrogen, methanol, etc. By the combustion of fuels or gases like hydrogen, methane, methanol, etc., they produce energy. Energy means electrical energy. Okay, so galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. to electrical energy. Such devices are called fuel cells. They are eco-friendly, they are pollution-free, and one example of fuel cell is hydrogen-oxygen fuel cells, which is mainly used in Apollo Space Research Program. Okay, hydrogen-oxygen fuel cell, H2O2 fuel cells, mainly used in Apollo space research programs. And you need to keep in mind the apparatus of hydrogen oxygen fuel cell. This is the apparatus. When you are asked to describe fuel cell, okay, you need to describe what it is, because it's very important to describe what fuel cell is, the apparatus, okay, the setup of fuel cell, the reactions taking place in fuel cell. So in fuel cell, this is the anode, this is the cathode, and here we have electrolyte. To the anode side, we are bubbling H2. To the cathode side, we are bubbling O2. And due to the reaction taking place in fuel cell, we have H2O as byproduct. So as H2O is a byproduct, it is completely eco-friendly and pollution-free. Okay, it is completely eco-friendly and pollution-free, and the water, the H2O from fuel cell can be used for drinking purpose. It is having high efficiency and it is also eco-friendly. Corrosion. Corrosion is the last topic of electrochemistry. So I guess you're all happy. After the 4 parts of electrochemistry, we're going to wind up the session with topic corrosion. You might have seen that in iron equipments, a rusting is formed, right? A rusting of brown color, black color, orange color, okay? A mixture of such colors are usually seen on iron equipments, equipments like utensils, etc. Or in the buildings, etc. Also in silver, you might have seen that a black color after some when you wear silver chain or you use a silver bracelet or a silver anklet, after some months of using, you might have seen a black color is formed on the top or outer surfaces of silver. Or if you have used copper and bronze utensils at home, you might have seen a green color coating forming. It's all due to corrosion. And what is corrosion? Corrosion means it's actually when the metal come in contact with air, the atmospheric particles, water vapor, a metal oxide layer is formed on the top surface or the outer surface of the metal. Okay, if this is the metal, let it be iron. Okay, when it react with water vapor or any substances like that, air or atmospheric phenomena, other phenomena, a coating is formed. A metal oxide coating is formed. An oxide of iron itself, okay, the oxide of same metal coating is formed on the outer surface. That is corrosion. So how can we overcome corrosion? To overcome corrosion, to overcome rusting, you can use paints, you can paint it, you can varnish it, or you can use anti-rust substances, or you can coat it with a substance of higher reactivity, a metal of higher reactivity. So in such a case, when the metal comes in contact with air and other atmospheric phenomena, rusting will happen to the higher reactive metal on below which the original metal is there. Okay, if iron is this, okay, if this is iron, and if I have coated it with a metal of higher reactivity, okay, this is a metal of higher reactivity. When it come in contact with the water vapor and air, when it come in contact with the water vapor and air, nothing will happen to the iron inside, but who will undergo rusting? The higher reactive metal on the top surface. Hope it's clear, and this chapter is over. We'll come again with the question section, the NCRT problem solving section, the previous year problem solving section. We'll do a part 5 of such problem solving or the problems. So stay tuned, and we'll meet in another class. Bye bye.